Okay, good evening. It's night time this time. Usually I talk to you in the morning. And very often I zap through lectures very quickly because I want to get it all done within a half an hour. Now this one I'm going to go more slowly at because there's more in it than the textbooks tell you, right? So I'll take my time. It's just to do with products within vectors. We're still on vectors. I'm just going to call it vectors. I noticed nobody was really following the total college course, so isolated topics seem to work better. So this is vectors, but products. Products are when you multiply things. Now with numbers, if you multiply two numbers, a times b gives you b times a. 2 threes is 6. 3 twos is 6. It means that, you know, it's commutative. But if a times b is negative b times a, that's anti-commutative. You get the negative of the other. That's just terminology. Terminology tells you absolutely nothing. Feynman didn't like terminology, but terminology is important when you're trying to communicate ideas. All right. So for vectors, in vectors we have three forms of multiplication. Now I'm not going to write the word vector all the time, I'll just write down the V with the symbol underneath it. V is just a vector, or is a position vector, which is a very special vector. When you put a hat over it, it means a unit vector. It means that the magnitude of that vector is 1 unit. Now in vectors, the first thing you do is you can multiply the vector by a scalar. Second thing you can do, you can take two vectors, multiply one by the other to get a scalar. Third thing you can do, and that's all you can do, is to take one vector, multiply it in a way by another to get another vector, not a scalar. And this is called the dot, or scalar product, the cross, or vector product, because of the dot and because of the cross, because of getting a scalar or because of getting a vector. Very clear, very simple. Okay, so let's deal with multiplying a vector by a scalar. Now I'm going to drop the hats over the unit vectors in terms of i's and j's. These are Cartesian vectors. Cartesian vectors have I, j's and k's in the x, y, z direction. gradually wean you away from ij's and k's and call them ex, ey, and ez. Sorry, ex, ey, and ez. I want to get you away from this notation. I don't like it. It's in the tradition, whatever. So we have v equals 3i plus 4j. Now what we want to do is multiply this guy by a scalar. So we go 2 times that vector. Or we could go v equals half of that vector. Or we could go v equals negative 3 times that vector. This makes it vector in the negative direction of it. If the vector is this way, this one is going to be this way, but 3 times as long. This one here, if the vector is that way, the next one, multiply by half, it will just be half as long. This one and this one are the same. So we just go 2 3s is 6, 2 4s is 8, and we get a vector 3i plus 8j. Let's see what that looks like. Well, there's the first vector. There's the second vector. Just a vector twice as long, but in the same direction. Let's see why. A vector of length 10. The original vector had a length of 5. This one is twice as long. The new vector, when we multiply by a scalar, is rescaled. That's what we mean by multiplying a vector by a scalar. Now suppose that we were multiplying by negative 2. It's going to have the same length, but it's going to be going down this way because it's going to be minus 3, negative 3, negative 4, and then to negative 6, negative 8. In this quadrant, it's just going to be in the opposite direction. But if so that's multiplying a vector by a scalar. Now I like to do things, no fancy, PowerPoints, no fancy graphics, no colors even. I have a couple of colors here. I use them on rare occasions. Sometimes I make a little mistake, so you can keep on top of that. I try to keep on top of them myself. Calculation ones, because I do everything live off the top of the head, and I don't leave any stone unturned. I've seen a lot of the videos on YouTube, and people skip 10 steps at a time, and the students think they're learning something, but they're missing out on an awful lot of stuff, unless they're very smart. But if they're like me, and we have to work through a step at a time, because that's how you do things, one step at a time. One step at a time. When you're making calculations in physics or mathematics, you do it one step at a time, but you let your hands do the calculation. Don't do it in your head. You can daydream and do calculations. So the next one we're going to do is, we covered that. We're going to do the dot or scalar product. After that, we'll do the vector or cross product. I'm limited in board space, so I'm going to clear everything. I used to love teaching at university when students would come around and then they do the evaluation of the teacher, and they used to You know, students who struggled always complained about two things. He moves too fast, he makes mistakes, and his handwriting is terrible. But the students who did well say, well, he teaches the course as opposed to PowerPointing the course. So the next one is, I'm having a glass of wine, so the scalar product. So we take two vectors, we multiply them together to get a scalar. Lambda is a good scalar. Here's some Greek letters. Start you off. Alpha, beta, gamma, delta, A, B, C, D. Let's put in a few more. That's enough. Lambda, pi, alpha, beta, gamma, delta. We use Greek letters all the time because we run out of Roman or any other kind of letters. So we need to go this dot this to give a scalar. We define it as follows. We'll take a vector A and multiply by vector B. Now I'm keeping the hats today, or just for this line. On the next line I'm going to lose these hats, just because it's tedious in terms of notation. And the K's are unit vectors. Now the unit vectors look like this. They're at right angles to each other. We're going to define the product such that the magnitude of A and B, the A dot B is going to be the magnitude of A times the magnitude of B times the cosine of the angle between them. So that I dot I, because it's going to be 1, magnitude of I, 1, magnitude of I, cosine 90, which is 1, which is 1. So I dot I is 1, J dot J is 1, K dot K is 1. If we stick to this definition, and we do, we put this in by hand. We define this to be the case. However, here's something. I'm terribly sorry. I made a mistake. It's cosine of 0. The cosine of 0 is 1. Now, if I take I dot j, then I go 1 is the magnitude of I, j is the magnitude of j times cos. Now, what's the angle between I and j? Here it is here. It's cos 90. And the cosine of 90 is 0 degrees. So this is 0. Similarly for I dot k and j dot k. In other words, if I and j are not the same unit vectors, the product between them is going to be 0, and we're going to use this over here in 1 second. So I'm going to do the distributive rule. So we go this times this vector plus this times this vector plus this times this whole vector. It's a distributive rule. In other words, I'm using distribution. This is in 2 dimensions. I just did it in 3 here. So let's see what's going to happen. We have an I and a j and a k. I times any of the j components, they will drop out. They will be 0. I times any of the k components will also be 0. Here we have j times the I component will be 0 because you're going to go j dot I. K times the I component down here is going to be 0 because k dot I is 0. So the only components that are going to survive are when we have an I dot I, or a j dot j, or a k dot k. Because anytime you have an I dot j, it's 0. Anytime you have a j dot k, it's 0, and all so on and so forth. Now these terms are all 1. So I just get a x b x plus a y b y plus a z b z. So a dot b means you just take each component separately and multiply them. And that's how we operate the dot product, the scalar product. Now this is going to be a number because that's a number times a number, a number times a number, a number times a number, add them up. So it's some number. Let's do an example. Clear the board and do an example. Now we define this just to obey this rule. I'm also going to simplify my notation. Instead of writing magnitude all the time, I just write the letter itself. That would be a vector, and that will be its magnitude. That keeps the notation simple. It's very useful to simplify your notation. Do a check. Just checking to see if the camera was working. Now, as a student, your job is to pay attention to details within the lines. I try to state everything, but it's not possible to state every little detail. When you work through problems, you will figure out your own little details that you will find to be important. I have many in my head, from being a student, and over the years I've accumulated more. But, you have to do it your own way, and then you can make up your own things that I never thought about, or anybody else for that matter. Now, very often we work only in 2 dimensions. So I'll go back to the 2-dimensional case. So we have 2 vectors. A equals 2i plus 6j, b equals 8i plus 3j. and they're all in the first quadrant, I could have thrown this one in with negative signs and mixed them up. I just want to keep it simple for now. So 2, 6 is going to be a vector that ends on the point 2, 6. So it's approximately, no, it's not quite like that. So it's going to look kind of like that. And this one is going to be 8, 3. So that's going to look kind of like that. Now I'm going to tell you that the dot product is going to be the projection of one vector onto another. Actually, I'll leave that for a separate lecture. So in the JY direction, the vertical direction, and the IX direction is the horizontal direction. So 2 8s is 16, 6 3s is 18, 6 and 8, 16 and 18 is 34. So this is a scalar of length 34. And the lengths of these vectors are the square root of the component squared. 2 2s is 4, 6 6 is 36. 4 and 36 is 40, so take the square root of that. 8 x's is 64, 3 3s is 9. So the length of this vector is square root of 73, and I'll work it out just to keep it there for use. Now I've rounded off, these are not exact, but that will do. So, A dot B has a value of 34. The magnitude of A is 6.3, the magnitude of B is 8.5. We found the scalar product, but now we can find something else. I want to find the angle between A and B. What is this angle here? Well, we have the definition. A dot B is AB cos theta. So therefore, cosine theta is A dot B over the magnitudes product. So that the cosine of the angle between them is 34 divided by these two numbers, and we'll figure it out. So that the cosine of the angle between the two vectors is 0.63. So on your calculator, you can say that the angle itself is the inverse cosine of 0.63, and your calculator tells you how to do this. we just go, 0.63 is on the calculator already. So we go, there's cosine, but slightly above it we go second function, cos, and I get 50.58 degrees. So therefore, these two vectors, and you can see even with my rough diagram that the angle is roughly like that. So now we've done the scalar product. There's more to the scalar product, but for this course that's all you need. In fact, for most things that's all you need. You need to know how to work it out. Just multiply the components and add them up. And you need to know to be able to find the angle between the two vectors. It's useful to be able to do that. Now the next one we will look at is the cross product. And I think I'll do it as a separate unit in 1 second.